Okay, so we were about to do the angle between the Fn and its lever arm. And so it should be alternate interior. Here's the F normal of the house. Here's the lever arm. It should be the same as this one down here, right? Alternate interior angles are said rule. So it's going to be 53.13. Make that a little bigger. All right, then you punch all this in your calculator carefully. And when you do, you should get 353.16 newtons. And what do we know? We know from our sum of the forces in the x that this is equal to the friction on the ground. Okay? And so we're looking for mu. So we know FFR is equal to mu Fn. So mu of the ground will be equal to FFR of the ground, which we just found, over the normal of the ground. So this 353.16 newtons. And remember we said over here, normal of the ground was m of the ladder g plus m of the person g. So 12 kilograms times 9.81 meters per second squared plus 60 kilograms. Gotta run out of room there. 9.81 meters per second squared. Okay, and when you do that, you should get 353.16 over 706.32 newtons. So mu ends up equaling a nice pretty 0.5. Okay, number 5. Number 6 is another ladder. Here it is. It's a 10-meter long, 12 kilogram ladder, and Romeo is climbing it. It's angled at 60 degrees, and Romeo is climbing it to reach his true love's window. His mass, Romeo's mass, person, is 80 kilograms, so he's heavier than the firefighter. And the coefficient of friction between the ladder and the ground, mu, is 0.35. Okay, how far up the ladder does he make it before the ladder begins to slip? So it's a uniform ladder, so we know Fg of the ladder is halfway along its length, but we don't know where Romeo is. Okay, so that's what we're looking for. We're looking for R of the person. And again, it says that you can assume there's no friction at the top. Okay, so this will be the normal of the ground. This will be the friction of the ground. This will be the normal of the house. Okay, so again, we can go in the x direction. Sum of the forces will be 0, and there's only 2. F friction of the ground minus F normal of the house equals 0. So F friction of the ground should equal the normal of the house again, which at the moment we can't find, but it should be equal. So then we go to sum of the forces in the y, also equal to 0. And again, it'll be F normal of the ground minus Fg of the ladder minus Fg of Romeo equal to 0. Always solving for normal of the ground. So equal to m of the ladder g plus m of the person g. And again, you could find this if you wanted to, or you can just leave the letters. Okay, so let's just leave the letters. And let's go to sum of the torques. Equal to 0. Again, a torque from the normal of the ground, a torque from the, let me make this friction of the ground, a torque from the normal of the house, a torque from the ladder, a torque from the person who is Romeo. Again, I would suggest pick your pivot point down here at the bottom. These two will go to 0 because if the force runs through the pivot point, its R is 0. And so when you fill in RF sine theta, the whole term goes to 0. My pivot point is down here. F normal of the house is going to make it rotate counterclockwise, so it'll be positive. And the two weights will make it rotate clockwise, which will be negative. So positive, negative, negative. So R normal of the house, F normal of the house, sine theta normal of the house. And for Pete's sakes, put subscripts in. For those of you that are a little less than careful, if you just write all R's and F's, you won't be able to keep track of which one's which. So put subscripts in here. So R of the ladder, Fg of the ladder, sine theta of the ladder, R of the person, FG of the person, sine theta of the person. And I don't think I said this yet, but notice that these two F's are weights because they're dependent on the ladder and the person. But the normal of the house is not an FG. It has the amount of force that the house pushes back on the ladder with has nothing to do with the house's weight. Okay, so it's just an Fn. This time we're solving for R of Romeo, so I take this whole term over. So this would become R normal of the house, and F normal of the house is really friction of the ground. Sine theta normal of the house minus R of the ladder, M of the ladder, G, sine theta of the ladder, and that's going to be equal to R of the person, M of the person, G, sine theta of the person. Okay, but this, and then we want to solve for R of the person. So we're going to divide by M of the person, G, sine theta of the person. But this normal of the, or force of the friction on the ground is really mu normal of the ground. Sine theta normal of the house minus R of the ladder, M of the ladder, G, sine theta of the ladder. And what is normal of the ground? Normal of the ground is this. And so here we have R of the person is equal to R normal of the house, mu, M of the person, G, plus M of the ladder, G, sine theta normal of the house, minus R of the ladder, M of the ladder, G, sine theta of the ladder, over M of the person, G, sine theta of the person. So you could have just, down here you could have gotten this value, multiplied it by mu, and got your friction of the ground, and then filled it in for normal of the house. But in a question we're going to do later, I'm not going to give you, I'm going to ask you to find an M, so you would have to do it the way I'm doing it here. So I just thought I'd do it that way now. So let's fill in our numbers. Normal of the house is the full length of the ladder, which is 10 kilograms. The mu they told us was 0.35. And then this is going to be, the person was 80 kilograms times 9.81 meters per second squared, plus the ladder was 10 kilograms, kilograms, times 12 kilograms times 9.81 meters per second squared. And then close this bracket, and then this is sine normal of the house, which is the 60, minus, at a room, R of the ladder, a 10 meter long, that's what screwed me up, this is meters, a 10 meter long uniform ladder, so the R of the ladder should be 5 meters. Mass of the ladder is 12 kilograms times 9.81 meters per second squared. Angle for the ladder, if we look back, this guy, so it should be 30. Sine of 30. And then all of this gets divided by mass of the person, 80 kilograms, times G, 9.81 meters per second squared, sine of the person, which will also be 30, right, because it's this one. Now, to save some marker ink and some space, you could have canceled out all the 9.81s because the G's are in every term up here. But we didn't, so you got to calculate it all out. Carefully punch this in your calculator, and you should get an R of the person to be 6.22 meters. Okay? And there it is. All right, so those are your two ladder questions. I also asked you to do, whenever we get to the yesterday's videos, I asked you to do 3 and 4 on the back side of the sheet on the more torque sheet. They are not ladders. No, I think it was 2 and 3. Sorry about that. It was 2 and 3. Okay, they're not ladders. And so the next video we'll go over both of those.